Hello, everybody, and welcome to another wonderful day of chemistry. So, last time we talked about how we could use entropy to describe isothermal and adiabatic expansions and compressions. So, today we're going to be looking a little bit more in detail of how we can look at both reversible and irreversible expansions, specifically how we can determine their entropy. Now, when we're doing this, what we can do is start with our generic definition of the um, entropy of a system as being based on the reversible heat to drive a process and the temperature of the system. Now, importantly, we often want this to be done at isothermal conditions. That way, that temperature isn't varying and our integral is nice and easy. Now, the nice part is that if we've got a reversible, if we're assuming the heat is reversible, then we can go ahead and substitute in our equation for the reversible heat that we covered in last chapter. And in this case, what we find is that it's going to be based on the natural log of the ratio of the final and initial volumes. Now, what's very important is that note, here we don't actually have to assume that this expansion is in and of itself reversible because the entropy itself is defined on the reversible heat. So whether we're looking at a reversible or an irreversible expansion, this will always be the expression for the entropy of an expansion or, again, a compression, which is really nice because that means that as long as I know the initial and final volumes, I can determine the molar entropy. And again, multiply it by moles and you get the size extensive entropy. So this is actually a very simple and powerful expression that we're going to use a lot. Now the problem is this tells me about how much entropy I have in the system. But as you've noticed, what we often care about is the entropy of the universe because we want to determine the favorability of a system. So for that, we need the entropy of the surroundings. Well, it turns out the easiest way to get that is going to be under reversible conditions because the entropy of the surroundings is based on the heat of the surroundings. Now, if I'm reversible, the heat of the surroundings is just going to be the negative of the heat of the reversible heat, which then means I get to substitute in this same volume ratio for the reversible entropy of surroundings. So this is actually fairly nice because we can use this to determine the overall favorability of the system. And now if I add these two systems together, note they're the same exact expression with just a flip sign. That means they'll end up canceling out, and the total entropy for this expansion is 0, which makes sense because if I'm looking at a reversible expansion, then that means the entropy of the system will be 0 because it's reversible. It means it's not net favorable in terms of expansion or compression. So again, this is a good way you can look at, this will be the minimum entropy that it will require to have an expansion. Now let's go ahead and look at the other end. What's the most amount of entropy I could get out of an expansion? And that would be a free expansion, where the system is expanding against no external pressure. But note in this case, the entropy of the system is still the same because the entropy of the system does not care whether we're reversible or irreversible. It will always be defined based on this natural log of the ratio of volumes. But what will change is going to be the entropy of the surroundings because that's going to be based on the heat. And if I have an isothermal system, again, assuming an ideal gas, that means my internal energy won't be changing. And if the internal energy won't be changing, that means that the heat is just the negative of the work. But it's a free expansion. And free expansions mean the system does no work. It's expanding freely against no opposition. And that means if we have no work, we have no heat. So it turns out that if I'm looking at a free expansion, the entropy of the surroundings is 0 because I don't have to pull in any heat from the surroundings to drive this expansion. The expansion literally just occurs naturally because there's no opposition. Now that has some fun consequences because it means our entropy, our total entropy, again, is just going to be that sum of system and surroundings, which means it's just the system. So that means I can get my change in total entropy just from the entropy of the system, which is going to be again be based on this natural log of the ratio of volumes. Now, if you think about it, I can't get any more entropy out of a process than this. Because again, it'd be hard to disorganize both the system and the surroundings. So this really sets the max entropy for an expansion, while the reversible entropy sets the minimum. And together these set our boundary conditions for expansion of a gas. And you can use the same general principles for compression. However, again, in that case, the entropy of the system will be positive, and then you'll have to be a little more careful playing with the surroundings. But again, nice part is if we're looking at an expansion, we can figure out the minimum favorability and the maximum favorability of this process. Now, we can apply these same ideas to other processes. Most notably, one of the more important ones we can deal with is the idea of phase change. One of the reasons why I paired this together is it turns out a phase change is also an isothermal process. In this case, I'm going from a solid, heavily organized, to a liquid, less organized, meaning I should see an inherent increase in the entropy. But one of the important parts is that as I undergo a phase change, at least for pure substances, it's all going to occur at a single temperature, which means we get to use a lot of the same tricks we did for our isothermal expansions and compressions. Now, in this case, it turns out that our entropy of transition is just going to be inherent in the process. The liquid or the solid will have a certain entropy, the liquid will have a certain entropy. Just by taking the difference, I should get the entropy. However, the entropy of the surroundings will still be based on how much heat it takes to drive this process. Because if I'm going from an organized to a disorganized state, it's gonna take some energy to break those bonds. So knowing how much I have to organize the surroundings will tell me a lot about how much entropy I'm losing from the surroundings. Now, again, this entropy of the surroundings is going to be based on that heat that I pulled from the surroundings, which in turn will be based on the heat that went into that transition, with again a notable negative sign, because if heat goes into the system, it's lost from the surroundings. Now, this means I can go ahead and insert this into my universal entropy equation. Getting the total entropy is just going to be based on summing together the inherent entropy of that transition, or in this case, fusion, and then subtracting out that heat of fusion. Now, here's the important part, that if this is going to be an isothermal process, that means that T isn't changing. And then suddenly taking the integral of the system is actually rather simple. I just get to throw deltas on everything and drop the D on the heat term. So that means my discrete change in total entropy is going to be based on that entropy of the transition, which we still haven't figured out, and the heat of the transition. Now, this we have a little bit more luck with, because we do have some relationships that tell us about heats of transition. The problem is we have to constrain our system first, and this is a very common theme with dealing with that heat of surroundings. So if I have an isochoric system, well, then the heat of transition is just the same as the change in internal energy for, in this case, fusion. However, we often much more care about our isobaric systems. And in this case, we're going to be looking at the change in enthalpy. So if we know our change in enthalpy and our entropy of transition, well, then we can figure out how favorable the process is. Now, there's a last important case, and this one's kind of an interesting one, an adiabatic system. So if I have an adiabatic system, I'm removing any ability to pull heat from the surroundings. And so that means that this heat term drops to zero, and the favorability of the reaction is entirely dictated by the entropy of transition, meaning that if I'm in an adiabatic system, I'm only ever going to go from an organized phase to a disorganized phase. So fusion and vaporization are okay, and um, uh, condensation and freezing are not. All right, so now we have a good expression for an isobaric, which is the conditions we care about, for figuring out the favorability of a system. But what we haven't yet figured out is how can I determine that entropy of transition? Well, the trick here is we go ahead and just simply look for the one point at which we know the total entropy. And that's going to be when the system is in equilibrium, when the system is equally likely to be found in the solid or liquid phase. And this is again where we get lucky that these tend to be isothermal processes, because that's just going to be the temperature of transition. So for melting, that's going to be the temperature of fusion, or the melting point. And for vaporization, that will simply be the boiling point. But if you know the temperature at which the system is in equilibrium, and we know the enthalpy of that transformation, again, that vaporization or fusion, congratulations, you can find the corresponding entropy of transition. So for example, let's say we're looking at water. So if I'm looking for the fusion or melting of water, well, congratulations, the melting point of water is at 273.15 or 0 Celsius. So we can then plug this in, grab the enthalpy we figured out how to calculate last chapter. Remember, we had to do the temperature corrections to get this. Then simply taking the ratio, we end up with the entropy of fusion. And again, note, here we have slightly different units than we've gotten used to in enthalpy. So the units here are going to be about 19 joules per mole Kelvin. So again, using information we can find in tables, we figured out how we can calculate enthalpies of fusion and then entropies of fusion. So relatively simple to find these from first principles. However, one of the things we have to worry about is how can I find good entropies on their own? And so for this, we're going to try and figure out next time how to look at absolute entropies, also known as the third law of thermodynamics. It's our last one. Until then, take care.